In the past 2 weeks, we have been examining the eigenvalue question. And I hope I am relatively successful in explaining to the class that the eigenvalue question is an engineering question. It's not a mathematics question. Eigenvalues occur in virtually every engineering discipline. And I have told you, if you are working on stress analysis, the eigenvalues are the principal stresses and the eigenvectors are the principal planes. If you are in vibrations, the eigenvalues are the natural frequencies and the eigenvectors are the mode shapes. If you are in electrical circuits, you also have oscillations and resonances, and you have eigenvalues and eigenvectors there also. And mathematically, a tensor will transform a vector in an arbitrary manner. You will not be able to predict what kind of vector you will get when you transform it by a tensor. But when a tensor that is not a special tensor, such as a spherical tensor, an identity tensor, or an annihilator tensor, and any of those special cases, when it transforms a vector without changing its direction, then there is a special case. We call that kind of vector an eigenvector, and the magnitude of the scalar multiplier is the eigenvalue that is associated with that process. And those have physical meanings. And many times when engineers are looking at a tensor, what they are really looking for are the characteristic values, which are also called the eigenvalues. So that is the eigenvector, that's the eigenvalue question. And we remember that we compared vectors and tensors. Remember that I said virtually everything that happens to vectors also happens to tensors. You have the basis, Cartesian basis vector, there are 3, for tensors there are 9. The component form is like this. And then the evaluation of the component is by taking the scalar product with the coordinates. Similarly, for tensors, again, you take the scalar product with the coordinates, but the scalar product of a tensor is defined in a different way than that of a vector. Vectors have magnitude, so do vectors. There is a scalar product of vectors, and there are 2 scalar products of tensors. There is orthogonality when the scalar products become 0. There is also orthogonality when the scalar product of tensors are 0. The 0 element in vector analysis is called the 0 vector. It has 3 zeros. 0 in the x-axis, 0 on the y-axis, 0 on the z-axis. So you cannot replace a vector 0 with a scalar 0. They're not the same thing. Similarly, a tensor 0, also called the annihilator tensor, has 9 zeros. So, and we use special symbols to represent them. For the vector 0, we use the small letter O that is bolded. Then the annihilator tensor is the large letter O that is bold. Then you have the following products for vectors: multiplication by scalar, the scalar product, also called the dot product because of the symbolism of that product. And then you have the vector product, also called the cross product, again because of the symbol used for that product. Then the tensor product, also called the dyad or the dyadic. Now, those are the products that are available for vectors. When you get to tensors, if you can have 4 products for vectors, there are up to 30 different kinds of products that you can get when you are dealing with tensors. But out of those, we are only interested in a few. Only a few. One is the multiplication by scalar, the operation of a vector on the operation on a vector, the composition, and the scalar products. There are other products that are tensor products that we are not dealing with at this time. And we've talked about the eigenvalue question. And we said, if a vector can transform, if a tensor transforms a vector, if you use 2 vectors that have been transformed to formulate an area, the area is transformed by the cofactor of that tensor. If you use three vectors to form a parallelepiped, then the volume of that, the volume occupied is transformed by the determinant. And those three things, when you start with the trace, and then the cofactor, and then the trace of the cofactor, as well as the determinant, constitute what we call the scalar invariants. They are scalar functions of the tensor, and they are critically important. So we've looked at that. We've looked at the eigenvalue question. We've looked at the characteristic value, and we have calculated it for some situations. And we showed how to use Mathematica to do the calculation of transformations. And then when it becomes an eigenvalue, we saw that it will just multiply it by a scalar value. Form of a scalar, of a transformation that is showing us the eigenvector and the eigenvalue. And then we now went using the fundamental law of algebra to explain how you can now get that eigenvalues and then subsequently get the eigenvectors. Last week, it was difficult for some people to appreciate that if we expand this equation here, we are going to get a cubic equation in the lambdas. And in that cubic equation, you are going to have the trace of the, you are going to have the trace. First of all, here you have the determinant, here you have the trace of the cofactor, and here you have the trace of the tensor itself. And there is a multiplication factor here, which is the triple product A, B, and C. This is the scalar triple product. If you divide this all around, then all those traces become clear, and the determinant become clear. And because some people didn't get that, I went through some extra work to prove those things to you. And then I hope by now, you can now recognize that this is the characteristic equation for any tensor, where the lambdas are the eigenvalues, and the I1, I2, and I3 are the invariants. I1 being the first invariant, which is the trace of the tensor. I2 is the second invariant, which is the trace of the tensor's cofactor. And I3 is the third invariant, which is the determinant of the tensor. And this is another way to write the same thing. The same thing here. Instead of I1 here, you say trace of T, trace of the cofactor of T, and trace of the determinant. And this is the characteristic equation. In this cubic, the zero here is a scalar zero. If you root in this equation written here, the zero here is a vector zero. So that leads us to the important Cayley-Hamilton's theorem. And it will lead us to what is called the spectral form. The Cayley-Hamilton's theorem, eigenvalues and eigenvectors allow us to write a tensor in another additive decomposition called the spectral form. Now I say another additive decomposition. Was there a previous additive decomposition that we know about? If there is, let me know. Go to the chat room and tell me what additive decompositions you remember with tensors. What are the additive decompositions you know? I'm in the chat room waiting for you. Those of you who are very slow and lazy to answer me in the class, I hope you know I'm taking record of all this. And those are your opportunities to get extra marks at the end of the term. You know, I don't add marks for students. It's only marks you get. Yes, there was another additive question. Which one? Then tell me. What? Ugochukwu? You said there is. Which one? That shows that this class, you people have not been paying attention and you have not been going to do your continuous assessment because you are so slow in getting this. Bulutife, completely wrong. Inner product is not an additive decomposition. Okay, since the class is very, you can decompose a tensor into its symmetrical and anti-symmetrical parts. And those constitute an additive decomposition, because when you add the symmetrical to the anti-symmetrical part, you get the full tensor back. You can also decompose a tensor to its spherical and deviatoric forms. So if you add the spherical part to the deviatoric part, you get the full tensor. But there is still one more additive decomposition that I have not talked about. There are at least 4 additive decompositions. I'm telling you one just now, but there are 3 I've told you before. I've named 2. I want you to name another one. What is another additive decomposition you can look at? There are 4 ways to additively decompose a tensor. Well, that's Kamal. I'm talking of the one I've taught you already. I've not taught you about that one. Well, you are forcing me to go back to show you the old notes, because I'm not happy at this dullness. I'm not happy at all at this dullness in the class. So you are showing that you are forgetting things so quickly. I don't even remember how long ago we did this. So let me try and open another file. Okay, decomposing tensors in week 8. So first of all, we can decompose a tensor to its components. So components are the weights. This turns the tensor into a weighted sum of up to 9 dyad bases. So that is an additive decomposition. When you turn, just the way you decompose a vector to ij and k, decompose a tensor into 9 components on the 9 dyad basis. That is an additive decomposition. 3 other additive decompositions are possible. The symmetric and skew parts, that's an additive decomposition. The spherical and deviatoric part, that's another additive decomposition. And the spectral form of eigenbases is the 4th additive decomposition. I have taught you the first 3. I was going to teach you the 4th one today, but you have forgotten the first 3. And this is how to break a tensor into its spherical and deviatoric parts. We did that in week 8. So this is how to compute the spherical part. This is how to compute the deviatoric part. And I showed that when you add the 2 together, you recover the tensor itself. Then from every tensor S, you can create the symmetric part and you can create the skew part. And the tensor itself is the sum of the symmetrical and the skew parts. So when you add the 2 together, you get it. So the symmetrical and the skew give you an additive decomposition. So the additive decompositions are breaking into components first, second, deviatoric and spherical parts, third, symmetric and skew symmetric part. Those are the skew symmetric is also called the anti-symmetric part. So those are the 3 ways you can decompose tensors. But we're going to go to another one today. Let's see. 7 should let me turn this off. And which one is this? 6. Now let me turn this one off. And then we're back to where we are now, which is get it from the current slide. So eigenvalues and eigenvectors allow us to write a tensor in another additive decomposition called the spectral form. 9 components of a regular tensor become 6 when the tensor is symmetric. In spectral form, the tensor is reduced to the eigenvalues in terms of the eigenvector dyads or eigenbases, and it is a much easier form. We'll get to that. But before we do that, let us take the Cayley-Hamilton theorem, which we'll be invoking over and over. Every tensor satisfies its own characteristic equation. Remember this characteristic equation we have here, this cubic. So instead of this being an equation that gives us the eigenvalues, we can replace lambda cubed by t cubed, the tensor itself cubed. And the cubing means that you are composing the tensor 3 times. You multiply the tensor in a composition by itself and by itself. That is what gives us t cubed. And then here it is a composition of 1 time. That is t squared. and then this is T, and then you now have here, instead of I3, you have I3 multiplied by, instead of I3 being a function of T, you have I3 multiplied by T, and the 0 here is an interesting one. So let me go back here. So this is the same spectral form. Unlike before, we are not, I1 is still a function of T, but here it is multiplying T squared. Here is multiplying T, and here you have to have the identity tensor, and here, what do you have? I want you to tell me on the chat room, why do you have to have the identity tensor here, and what is this element here? What kind of 0 do we have on the right-hand side? Remember, in the equation, there is no identity tensor in this term, and this 0 is a scalar 0. So explain to me why, in the form we have now, why do we have to have the identity tensor in that place? What is this one doing here? And what kind of 0 is this? James Utokton said, because we are adding tensors in this case, and the result should be an annihilator tensor. So the right-hand side must be an annihilator tensor. Okay, what about this I? What is this one doing here? Why not just I3? Is this class sleeping? Yes, but what if is the determinant? And so why does that justify the application use of I? Okay, you are not doing well today so far. This equation here, is it a scalar equation, a vector equation, or a tensor equation? This equation here, the characteristic equation, is it a scalar equation, a vector equation, or a tensor equation? Yes, there's a question on board for the class. There's a question there in the chat room. Is the characteristic a vector equation, a scalar equation, or a tensor equation? Okay, Ginika said tensor. John Ashaolu said tensor. David Adigo said tensor. Israel Olawi said tensor. Oreoluwa says tensor. Christian Ikega says tensor. Kamal is the only odd man out. He says it's a scalar equation. Is there anybody that is taking the minority position of Kamal? Kamal. Is there anybody else? Ugochukwu, you are siding with Kamal, okay? Who else? Okay. All of you that say it's a tensor equation are dead wrong. This equation is a scalar equation. It's a scalar equation. What we have there is lambda, which is a scalar cube, plus I1, which is a scalar function of a tensor. It is a scalar function determined by a tensor, but it is a scalar. I3 is the determinant of the tensor, it's a scalar. I2 is the trace of its cofactor, it's a scalar. So the 0 here is therefore what type of 0? A scalar 0, vector 0, or tensor 0. Okay? So the right-hand side of that equation must be a scalar 0. That's correct. So that is what is happening here. Okay? So we are going to go to another one. Carly Hamilton says every tensor satisfies its own characteristic equation. Now, here, I2 times T is a scalar multiplying a tensor. What do you have when a scalar multiplies a tensor? Is the Cayley-Hamilton theorem, scalar equation, vector equation, or is tensor equation? I want to see. I want more answers. Yeah, good. Okay, so that explains where there must be an I here, because if this is just I3, so you'll be subtracting a tensor from a tensor and adding another tensor and now subtracting a scalar. You cannot subtract a scalar from a tensor. It's not defined. So you multiply the determinant of the tensor with the identity tensor, so you get a spherical tensor here. So that every term in this equation is a tensor, and that's why the equation is valid. And the right-hand side has to be a tensor 0, because everything on that equation, you multiply a tensor in a composition by itself, you get another tensor. You do it again, you get another tensor. So T times T times T is a tensor. T times T is a tensor. T is a tensor. I3 is not a tensor, so we have to condition it with the identity tensor here to get a tensor, then gives us an annihilator tensor. So that is the reason why this I is here, and that's the reason why this O is a tensor 0. Okay, so you get that. Good. Move on. Now, this fact is used in continuum mechanics to obtain spectral decomposition of important material and spatial tensors. It is easy to show that when the tensor is symmetric, its 3 eigenvalues are all real. Its symmetric tensor has real eigenvalues. When they are distinct, corresponding eigenvectors are also orthogonal to each other. So the eigenvectors are vectors, but they are in mutual orthogonality to one another. It is therefore possible to create a basis for the tensor with a dyad basis of eigenvectors. This is called the spectral decomposition of a symmetric tensor. When the tensor is symmetric, its eigenvalues are real, and its bases are orthogonal. They form an orthogonal system. So, and when you normalize them, you have an autonomous system, and therefore you can now write T as sum of I is equal to 1, lambda I, Ni, circumstance Ni. Normally, you know, we don't use the summation sign. I want somebody in the class or people in the class tell me why we have no choice here, but we must bring in the summation sign. There's a reason why we must bring in the summation sign. Can you tell me why the summation? Why is there the summation sign in that equation? Why? We have stopped using the summation sign, but here we have no choice. James, you don't think you are wrong. It's not because of the scalar lambda. It has something to do with summation convention. Can you remember what the summation convention is? When we dispensed with the summation symbol. Ugochukwu, yes, we are summing, but if we were summing, we have been summing all this while without using the summation sign. We've been summing, but we didn't use the summation sign. We use the summation convention. Why can't we use the summation convention here? That's the question. Why are we not using convention here? Why are we explicitly bringing the summation symbol to do this sum? Or do we not need to? Could I have written it like this? Would this have been right? Remember that once we have a repetition, there is summation. So with that, would this have been correct? Will this have been correct? Is this class there? Is this class paying attention? You are making today's class exceedingly slow. We have a lot to do. And we have done 30 minutes without progress. You don't, even James Dotton, I'm happy that you say you don't know. Okay, why would it have been wrong? Why would it have been wrong to write it like this? Why would this have been wrong? Why did we have to bring in the summation sign? Okay, nobody got it. Nobody remembered. Okay, let me remind you. Summation convention is that anytime an index is repeated, there is summation. That is the summation convention. But that an index must not be repeated more than once. We now have a situation where an index is repeated. You see I here, I here, I here. So the summation convention is not applicable here. So we cannot use the summation convention to sum this. So we have to bring back explicitly the summation to be able to know that we have here lambda 1 n1 circumstance n1 plus lambda 2 n2 circumstance n2 plus lambda 3 circumstance n3, because the summation convention does not apply here. So we have to bring the summation symbol explicitly to do this summation. That is the reason. You will see that we don't normally use the summation sign if we could have just used the summation convention. But here, we cannot use the summation convention because this index is repeated more than once. Go back again and go back to the original thing when we discussed the summation convention. The index must not be repeated more than once. So once it's repeated here, it is repeated two more times, making 3. So the summation convention is not correct to use. And that is what forces us to use the summation sign. The normalized eigenvectors form an autonomous system in the spectral decomposition of in the spectral form, the matrix representation of the tensor becomes a diagonal matrix. the tensor has been diagonalized. So when you put a tensor in some textbooks call it the canonical form. When you put the tensor in that form, you say the tensor has been diagonalized or it is a canonical form. One example you've already seen is your stress tensor, where diagonalization creates coordinate system where your off-diagonal terms, the shear stresses vanish. The eigenvalues in this case are called principal stresses. The eigenvectors are the principal planes. Remember that the planes are determined by the normal to each plane. These eigenvectors are mutually orthogonal, so their normalized form are orthonormal. The above spectral decomposition is a special case where the eigenbasis forms an orthonormal basis. Clearly, all symmetric tensors are diagonalizable. A tensor that is symmetric can be diagonalized because it has three eigenvalues that are distinct, that are normalized and orthogonal to each other. Multiplicity of roots, when it occurs, robs us of this representation, and the temperature is no longer unique because two or more coefficients of the eigenbasis are now the same. The place is discoverable by an ingenious device called an eigenprojection. So what then happens when all roots are equal? The three autonomous vectors obviously constitute an identity tensor, and the unique spectral representation therefore becomes lambda n1, n2, and ni. So because the three eigenvalues are equal, instead of lambda 1, lambda 2, lambda 3, you can call all of them lambda, and therefore you take it out of the summation sign. It has no lambda again. And in fact, in this equation, in this last equation here, we can actually dispense of the summation sign because the summation convention is again applicable because you have a repeat of the dummy index only once. So the diagonalized tensor becomes a spherical tensor in this unique case, and the normalized eigenvectors is the identity tensor. In the second case, where you have two roots are equal, suppose lambda 1 is unique, where lambda 2 and lambda 3 are equal. In this case, you can still write the tensor as lambda 1 n1 circle times n1 because that one has its own eigenvector, but lambda 2 does not have any other eigenvector. So you just subtract n1 circle times n1 from the identity tensor, and that becomes the eigenvector of the that are equal. And this is another way that this thing can be written, and everything is still autonomous because this one is normal. This one, it can be said that what we have here, the n1, they still form a complete basis in this case. All the bases together will sum up to the identity tensor. The eigenspace of the tensor is made up of projectors, and the first projector is n1 circle times n1, and the second projector is the identity tensor minus n1, n1. Eigenprojectors in all cases are based on normalized eigenvectors of the tensor, and they constitute the eigenspace, even in the case of repeated roots. They can easily be shown to have these three properties. They are idempotent in the sense that if you take the multiplication of one eigenprojection with itself, it gives itself. For instance, CP1. If you multiply P1 by P1, you can test it out that you are still going to get P1. Similarly, if you multiply P2 by P2, you are going to get P2. I ask you to do that during your break, and I will ask you whether you just let me just do it for let us look at P1 times P1. Because the class is very dull today, so I am not sure that you are not dozing off. So let me just do this one. I'm getting a page. Let me get the page here. Home, new slide. So what I want to do is I want to multiply P1 by P1. Okay. So this thing, if this is P1, then what is P1, P1? P1 is a tensor. Then what is P1? P1. That will be equal to, now, class, work that out for me and tell me what the answer of this is. What's the answer of n1 circle times n1 multiplying n1 circle times n1? What is it? What is that? So class, tell me, anybody who does not now, who cannot see that this must be equal to n1 circle times n1, which is equal to p1. Okay, you can now see. Okay, good. We introduce the shadow transformation as if they were parallel rays of light creating the transformation. When this happens, it is called a projection. In order to establish the textual credential, we shall regenerate the same situation mathematically and introduce the projection transformation. So this is the projection transformation, and we can see that this is the projection tensor. We have done that. So conclusion here is that these eigenprojectors are idempotent. They are orthogonal. When you multiply any two of them together, you get the annihilator tensor, and they are complete. When you add all of them together, they give you the identity tensor. I just showed you for P1 and P1. Try it for P2 and P2. You see that P2 times P2 will give you P2. P1 times P2 will give you 0. P2 times P1 will give you 0. That is the annihilator tensor. I think what we will do is that at this point, we will take a break of 15 minutes and continue the lecture, because at noon, I'm going to start you with the week, I think week 10. So we're going to move to a new topic, which is tensor calculus. So I want to start that on a new note after the break. And we will come back exactly at noon. Please don't come late, because I'm starting exactly at noon. Thank you.